Hi everyone, thanks for checking out this video. So in the last video, we worked on downloading the data and then processing it to get it into these training and testing data sets. And then now in this video, we're gonna be actually using PyTorch to create a machine learning model that we'll eventually then use to train on this data and hopefully be able to make predictions. So yeah, there's going to be a video about how to make this PyTorch model. We're going to be using a type of model called a convolutional neural network. And so before we actually write any of the code, I actually wanted to recommend a video for you guys to like get some intuition about this, because I'm going to try to make this video as informative as possible, but with this type of model, the convolutional neural network, it really helps to be able to like visualize what's going on. And unfortunately, I'm just not good enough at like graphic design and animation to make a good animation of this. But I really recommend you check out this channel StatQuest video, kind of explaining conceptually what convolutional neural networks actually do. You can see this guy's made this like really nice animation of how they work. So in my video, I'm going to be showing you guys how to implement this in Python and like write the PyTorch code. But unfortunately, I just am not good at like making these animations. So I'm going to recommend this video to you guys, and I'll link to it in the description too. So if you guys want to get like a conceptual, intuitive understanding of like how these models actually work, I'm going to recommend checking out this video here. But okay, so what you guys are going to need for this video is this library PyTorch. It's a pretty famous Python machine learning library, probably the most famous one. So what you need to do is go to pytorch.org, and then you'll see a page like this, and then you basically need to just like select like what kind of machine you have, and yes, like what kind of machine you have and what you want to download exactly. But yeah, if you don't know what any of these are, then the default should be good. And then you're just gonna copy and paste this pip command here, and just put that in the terminal like that. Whoops, it's not actually trying to. Sorry, yeah, I was not trying to actually run that. Yeah, because I already have it installed. But yeah, if you guys don't have it installed yet, just go to this page, and it'll give you a pip command down here, and then just enter that into your terminal to get it installed. But yeah, okay, so let's get into the actual code for this thing. Okay, so first you're going to import Torch. That's what the PyTorch library is called when you go to import it. So that's just kind of like the general library that has all of these like machine learning tools for making these like neural network models. And then we're also going to say import torch.nn SNN. This is just a bit of a convenience thing. Like, since we already imported Torch, we could just call torch nn whenever we needed it. Like, we could just write it like that every time we need something here. But this is just a convenience thing, just to call torch.nn SNN, because yeah, this is the tool that has a lot of like the neural network functionality. So we're going to be using a lot of this torch.nn. And then we're also going to import torch.nn.functional sf. Again, this is just a bit of a convenience thing. Rather than writing this whole thing out, this will let us just write f. And then yeah, so that's all we need for now, actually. Oh yeah, before I forget, I'll just put the link to the StatQuest video right up here for you guys in case you're downloading this from my GitHub. Yeah, this is the link to this like StatQuest really good like conceptual explanation video with these animations. So yeah, I definitely recommend checking this out. But yeah, okay, the other thing we need too is, remember how I said in like the previous lesson, we want to always have our image size up at kind of the top of the file just to keep track of it. So we're going to have that also in this script here. Image size equals 50 pixels by 50 pixels. Yeah. Okay. So the way this is going to work, and the way we're going to like write this neural network model, is by making a class. So it's going to be a bit of object-oriented programming. Don't worry if you're a bit rusty with object-oriented programming, because to be honest, I'm also not like that good at it. I don't use it a lot in my like actual day job. I really only use it when I'm doing this kind of like neural network type work and some of my like side projects. Yeah, I don't do a lot of this kinds of like class definitions in my actual day job. So yeah, I'm also a bit rusty with it. But yeah, so we're gonna say class net. You guys can call it whatever you want, but I'm just gonna call it net so that it makes sense. And this is going to inherit from the nn dot module class, which is like the basic class for the PyTorch neural networks. So yeah, this syntax here, in case you guys forgot, this is just saying that we're making a class called net, which inherits from this other parent class nn.module. Okay, so then maybe you guys remember that when we're making a class, we need to have this like constructor method that we call underscore underscore init underscore underscore that takes like the self as its argument. So basically, this is the constructor that constructor. This is what gets run every time we make a new like instantiation of the class. So whenever we make a new one of these net objects like this, which we're going to do in a second actually, whenever we make a new object from this class, it's going to run this init constructor method to like initialize itself basically. Okay, and then the first thing we're going to say here is super dot init. So basically, this is calling the constructor of the parent class. Like we said, nn.module is the parent class. So this line here is basically saying like super. That's the parent class dot init. That's basically just running the constructor method for this parent class that we're inheriting from. So that, yeah, just to like properly initialize all the attributes for the parent class and stuff. Yeah, okay. So now what we need to do is we need to define some convolutional layers. And again, if this doesn't make sense to you guys, what I'm talking about with convolutional layers, again, I'm just going to keep recommending this StatQuest video. Because, yeah, it's like I said, like I'm trying to explain as much as possible in the code, but for these things, like it really helps to see like an actual animation of them. But yeah, so basically we're going to be defining a couple of convolutional layers. So yeah, I'm going to say self dot conv1. This is going to be our first convolutional layer equals nn dot conv2d, two-dimensional convolutional layer. Input size 1, output size 32, and I'm going to say kernel size equals 5. So just trust me on this for now. Again, if you guys are wondering like what the kernel size is, I'm just again going to recommend this video again to you guys here. Yeah, this explains like what the kernel is and like what the kernel dimensions are and stuff, and how the kernel like moves through the image kind of to like process it, I guess. But yeah, I'm just gonna say kernel size equals 5 for now. So yeah, it's basically the dimensions of the kernel that's going to be like moving kind of across our image. Okay, and then self dot conv. You know, it's going to be easier actually just copy and paste here. I think conv2. That's our second layer. And the important thing here is you guys can kind of play around with different input and output sizes, but it's important to make sure that whatever the output size is from your previous layer, that's also going to be the input size for your next layer. So like 32 is the output size of our first layer, so that means 32 is going to be the input size for our second layer. And then you guys could like play around with different sizes. You guys could make this also like output 32. I'm going to make it just output 64 here because that's what I've been kind of doing. It's been working okay. But yeah, when it comes to like defining the specific input and output sizes and like how many layers to use, there's not exactly any like right or wrong answers. Well, I guess there are wrong answers, but there's not. Okay, I guess there's wrong answers, but there's not exactly any right answers. Um, it's just a matter of like trying out different things and playing around with it. There's of course some like theory to it too, that you could like read up on about how to do it optimally. But yeah, it's kind of a matter of just playing around with it. But the important thing is making sure the output from a layer matches the input for the next layer. So this one is going to be the input is going to be 64 and the output is going to be 128. Okay, so I'm just going to keep it at 3. Whoops, be conv3. Yeah, 3 convolutional layers for now. I'm worried that like any more than that is going to just take too long to run for the purposes of this like tutorial. Yeah, so after a couple of convolutional layers, we need to get it to be we need to eventually get it back to like linear layers so that we can get like a linear layer to give us an output with an actual prediction. So I'm going to define 2 like fully connected linear layers. So I'm going to say self dot fc for fully connected 1 equals nn dot linear. I'm going to explain in a second how we're going to get this input size here, but for now I'll just put some question marks. And then output can make it whatever we want. I'll make it like 512. Because that's what I've been kind of playing around with and it's been working. And then fully connected 2 input size equals 512, matching the output from the previous one. And then okay, this is important. For the last layer, like the final layer that's finally giving you your output from this whole thing, you need to have the size match however many classes you have. So in our case, we have 2 classes. There's the melanoma images and then the benign images. So we're trying to make a binary classifier. So we want to have a final output of 2, so that it's basically giving like some confidence level of each one of these possible outputs. If we were trying to classify between like 5 different image types, then we'd make this a 5 here. But since we're making a binary classifier where there are 2 possible classes that the image could be, our final output here is going to be output size 2. Okay, so now we need to we need to get back to this part here. So basically, when you go from your last convolutional layer to your first linear layer, the dimensions get weird to the point that it's difficult to know exactly what size the input is supposed to be for this linear layer. So I found that the easiest way to like figure this out is just to pass some data like through the model and then just print out what size it is and what size we need and then update this here. So I'm gonna make this a 0. I'm gonna make this a 0 for now, but I'm gonna put a note to ourselves like to do need to get input size. So we're gonna eventually have to figure out what size input we need for this linear layer, and then come back and eventually like update the code here to make sure this is getting sized properly. But okay, so moving on for the second, and we're going to come back to this for sure because we have to. But yeah, moving on for a second, the next method we're going to define is going to be called forward. And by the way, this method has to be called forward. You can't play around with like making up your own name for something. For this to all work, it has to be called the forward method. So basically, this is gonna be the method that the input image like follows through all of these layers and then eventually output. This is like the forward pass of the neural network. That's how like the image data moves through the network and then yields some kind of output for us, basically. So it's going to take self and then x, where x is our like NumPy array image representation. Yeah, that's basically the image that we're passing through this thing. Yeah, okay. So basically we're in this method, we're going to be passing this image in X like through all of these layers basically. So for the first layer, I'm going to say I'll do it little by little, so before we like even reassign it. So I'm going to first say self.conv1x, basically just passing X through our first convolutional layer. And then so once we do that, we're going to do like a transformation on the output. We're going to say f.ReLU. So basically, the ReLU function, it sounds confusing. This is something like a little bit annoying about machine learning, is that sometimes they'll take like a really simple concept but give it like a fancy sounding name to make it sound like more complicated than it actually is. But basically, the ReLU function, all it does is that you give it a number, and then if the number is positive, it just keeps that number. And if the number is negative, it makes it 0, basically. So basically, this function f.ReLU, if you give it a number or like a tensor or like an array of numbers or something, basically says any positive number, it just keeps the way it is, and any negative number, it makes it 0. So it basically just, it applies this kind of like transformation to whatever data you're giving it. So yeah, negative numbers become 0, positive numbers just stay themselves. So yeah, it sounds like something confusing, like ReLU or whatever, but yeah, it's not confusing at all. It's like really the simplest thing ever. Yeah. Okay. So yeah, we're going to use that kind of transformation on the output of this first convolutional layer, and then we're going to do what's called a max pooling. So I'm going to say f.maxPool2D, and just wrap this entire thing in this like max pooling here. Whoops, I think I did something. Sorry, I got screwed up with my parentheses for a second there. But yeah, max pooling. First argument is this like output of this ReLU, and then the second argument is going to be just a tuple with 2, 2. Basically saying we want to do like 2 by 2 max pooling. Again, if you guys don't know what max pooling is, like again, I recommend this video for you guys, the StatQuest, really good explainer. But also maybe I can like Google it here. Yeah, max pooling 2D. Yeah, it basically transforms the output like this kind of. Yeah, it basically does like a transformation on the output to kind of like do this to it, if it makes sense. Like each one of these things, like see 20 here is like the maximum of these numbers, and then 30 is like the maximum of these numbers, and then 112 maximum of these, and then 37 is the maximum of these. So basically, it does this kind of like transformation on the output. Again, if you guys want to see like a really nice animation, just check out the StatQuest video. I know I keep saying it, but I kind of feel bad that I can't make like a nice animation myself for you guys, so I'm just going to recommend this one to check out. But yeah, okay. So at that point, we can reassign, just assign it again to X. So we pass X through all of this, pass it through the first convolutional layer, then do the ReLU transformation, and then the max pooling. Oh, and by the way, this 2 by 2 thing here, this is also called a kernel. So we're doing a kernel in the convolutional layers, and also a kernel in the max pooling. So just some terminology for you guys. Okay. Yeah. So okay, going okay so far. So basically, that was our first convolutional layer. Now we're just going to do the same thing again. Again for the second one, pass through the second convolutional layer, and then again, same thing for the third one. Okay, so now the image data has been through all 3 of these convolutional layers. So at this point, we need to actually like, the next step is going to be passing it through the linear layers, but it's like I said, we need to get the size of this thing. So basically, I'm gonna like add some lines here. And we're gonna take these out before we actually like finalize this code. But just for now, I'm gonna add some lines, just like printing out the shape after each one of these. So I'm gonna print shape of X after the first convolutional layer, after the second one, and then after the third one. And the third one's going to be the important one, because basically the shape after this third convolutional layer is going to tell us what we need to make as the input size for our first linear layer. Yeah, because I know it seems like it should be 128, but it's actually not, because there's just other stuff involved. There's these like kernel sizes and max pooling, and there's a lot of like transformations being done here. So we actually don't really know what shape we're going to need for this input size for the linear layer until we actually print it out. So yeah, I'm just going to print out the shape here, and then import sys, and then sys exit trying to get shape for linear layer. Okay. Okay, so in order to actually get this, we need to actually like make up like a fake image just to pass through this thing, and then see what shape it is at this point. So I'm gonna first just define a net object just called net, and then I'm gonna say, sorry, I'm just gonna copy and paste in something for you guys. I'm gonna just make a test image. Just some random numbers, but the important thing is making sure it's the right size. So I'm just gonna make it, some random numbers in Torch, but it has to be the right size. It has to be 50 by 50, which we saved up here, 50 by 50 for this image size. And then I'm gonna say dot view. This is a way of like resizing something in PyTorch. I'm just gonna say like -1. I actually don't even really need that. This could just, you know what, I better just leave it in. I don't even think I need this -1, because the -1 is basically saying like just to be flexible with like how many images are being input, but we're only using one, so I don't even think I need this -1, but I don't want to change anything now because it was working, so I'm just going to not change anything. But I think we'd be okay even without this. But then rather than having it be 50 by 50, we need to actually be 1 by 50 by 50. That's just like a PyTorch quirk, I guess. But yeah, we need to make the shape of the input 1 by 50 by 50. But yeah, so this is just a test image, and we're just going to basically pass this through, pass it through the net. And so basically it's just going to get passed through the first layer, pass through the second layer, and then pass through the third layer. And then after the third layer, we're going to print out the shape of it, and then use that to figure out what shape we need to make, this input size for this first linear layer. Yeah, so hopefully this will work. I mean, we'll see. So hopefully. Whoops. Sorry guys, I figured out I'm in the wrong directory here. I need to, yeah, just give me 1 second. I just need to get back to the right directory. Okay. Okay. So yeah, we can say that it went through the first convolutional layer, and then it had this this output. Again, this is based on like there's a lot going on here. So this is based on like the kernel size and the max pooling kernel size and like these input layers and stuff. So there's a lot going on here, but yeah, the important thing here is this last part here, 128 by 2 by 2. So this is basically going to be something we need to flatten in order to use for the input for this linear layer. So the input size from this linear layer now is going to be 128 times 2 times 2. And basically it's just going to be flattened. It's going to be all these 3 dimensions here like flattened. And then it's just going to be like 1 dimension with like this length here, 128 times 2 times 2. Okay. And then we also need that. Oh, okay. So, okay. So now we're ready to proceed on. I'm gonna just comment out some of this stuff here. we're going to proceed on. So the next thing we need to do is we need to, like we've just seen, like the shape of X at this point is technically four-dimensional, really three-dimensional, because this first dimension is just like a quirk of PyTorch. But yeah, we need to get this to be the same number of elements but flattened, right? So we need this to be like only one real dimension, with like still this many elements, but like flatten this out. So what we're going to say here is x equals x dot view. -1, again, that's just telling it to be flexible in terms of like this first dimension size. And then the next dimension is going to be 128, like we said, by, sorry, not by, I'll just say times 2 times 2. Yeah, because we need to have this many elements, but just flattening out these 3 dimensions here. Okay, yeah, so from here we're ready to pass it through the linear layers. So we're going to say, again, we're just going to say like self.fc1x. That's just going to pass it through this first linear layer. Again, we're going to do this ReLU transformation. Again, don't get confused with the difficult terminology. It's kind of funny, even like ReLU, even it makes it even. It's almost. I'm getting a little bit sidetracked here, but this is almost like how I thought about numbers when I was in like 3rd grade, seeing like negative numbers for the first time. I was just like, oh man, this is too complicated. Just make all the negative numbers, make them all 0, and just positive numbers, they're okay. Negative numbers, just forget about them. Just make them 0. So it's actually, it's not only is it not complicated, it's like an oversimplification, because you're just like getting rid of the negative numbers and just making them all 0. So yeah, it's not complicated at all. Very easy. But yeah, so we're gonna pass it through this linear layer and then do the ReLU transformation and then reassign to be x. Last layer here, self.fc2, passing through this second and last linear layer. And then the real last part here is we're going to say x equals f dot softmax x. So basically the softmax function, basically it just takes whatever kind of numbers you have and makes them into a probability distribution. So basically we want our output to be kind of like a probability that the model assigns to being melanoma and a probability that it assigns to being benign. So basically this softmax is just saying like whatever kind of numbers we have here, just like make them into a probability distribution. So yeah, it applies this kind of transformation to it. Basically, just yeah, makes them into a probability distribution according to the size of these numbers here. Yeah, again, super simple thing that sounds like confusing terminology, but it's actually not that confusing at all. It's actually really simple. And then yeah, so from there we just return x, and then we should be good. Just checking to make sure got everything. Yeah, should be good from here. So from now, I think because this video is already getting a bit long, I think I'm going to save the actual like training of this model to the next video. But yeah, so I'd say just comment out this code for now. We don't need it anymore. Basically, we want this script to be like imported by other scripts. So basically, the whole point of this file is just to define this class, and then we're going to be importing this class into other files. So we don't actually want to run anything in this file. This is just defining a class that we're going to then read into other files. But yeah, so in the next video we'll show I'll show you guys how to actually like train this model on the data. Yeah, so thanks for watching and see you guys next time.